is Chaitanya Garwal, and I'm one of the TAs for your ELG 4125. My email is on the screen, or it's probably in the slides the professor has given to you. You can refer to them and always contact me via email. And if you have any questions, you need clarifications, we can always use Zoom or any other video conferencing software to meet up at the DGD time, and then we can discuss the problem and go over them. Well, for the first DGD, we're just going to do review for AC circuits, power triangle efficiency, and voltage regulation. Hence, it's going to be a little small one, maybe 30-40 minutes, maybe smaller than that. We'll see how this goes along. I might add some more problems as we go along in this DGD. So let's begin this. All right, first we'll begin with the AC circuits. First of all, we are always going to be dealing with the AC voltage in this course. And for this DGD, we are just going to be focusing on single-phase circuits. We will eventually move to a three-phase circuit where we're going to, basically three-phase power supply, generators, transformers, and we'll focus on that eventually. How the power is divided, the phase angles between them, and so and so. However, for the single-phase circuit, we have three major components in the circuit, or four, I guess. So we have the power source, first of all, then we have any resistance in the circuit, followed by inductance or capacitance. We will look at them individually and how each of these components affect the current and voltage in the circuit. So let's say we have a circuit just with the resistance. The voltage and current will be in phase to each other. That means that the voltage and current won't have any lagging or leading between them, hence the angle between them would be zero. I'll show you later in the doc like how it looks like, and then you can understand more. And then when we have L, that is inductor, the current always lags behind the voltage. It's because the inductance sucks the current out of it, slowing down the current consumption as towards to the voltage. Voltage keeps on going forward and the current starts lagging. However, when we have a capacitor, the current starts leading by 90 degrees. And same with the L. L lags behind by exactly 90 degrees. So it's the same thing, same concept, but just different. The current is leading the voltage by 90 degrees in capacitance. Current lags behind by 90 degrees when we have inductance. I'll show you next slides in next page in which you will see the diagrams of it and how the voltage and the current lags and leads. So here we are. So we only have the first diagram represents just the circuit with just the resistance. We see from the second diagram right here that the current and the voltage, they do not lag. They all are in sync. It's just the different values of them. So voltage is less, current is higher, hence we have two different graphs. They follow the sinusoidal graph, the sine function. It's always for them. And then we have the inductance, L. Here we see that the voltage started earlier and it's going ahead, whereas the current started slow and it starts lagging behind him. Eventually the current will be behind him by 90 degrees exactly. Same for capacitance, opposite for capacitance. The current starts early and starts to go ahead of the voltage. However, voltage starts slow and it starts lagging behind it. So hence current leads by 90 degrees in this case. Okay, so I might be going a little fast in this one, as you guys might have done this before. So let's look at the complex power right now. Don't worry about this at the moment. We will focus on this in a bit later. Okay, so we have complex power. So complex power is the combination of real power, which is in watts, plus reactive power, which is VAR, which is in terms of a useless power or just not used at all. However, when we are always calculating the complex power or just solving a single phase circuit, we generally focus on generally focus on VRMS value. The VRMS is, however, calculated as V peak times 1 over square root 2, or square root 1 over square root 2 could be written as 0.7071. So let's say you're given a circuit whose V peak is 20, or you're just given a graph that says V peak is 20 volts. Then you can calculate the VRMS for the calculation of the current or the resistance or so and so. You just do is 20 times 0.7071 and we get is 14.142. Hence, that's the value you use to calculate the current in the circuit or the complex power of the whole circuit. And I'll show you an example how we can do with that. Yeah, so just a basic example here. We have a 25 ohm resistance, V 10 volts VRMS. It's given to us, so we don't have to calculate at this stage. However, you can always calculate the V peak by opposing the formula. So just multiply by root 2 and you will get the peak voltage of the circuit. And we have an inductance. I'm not sure if you guys remember how to convert from Cartesian to polar form. So I have a review a little bit of here how to do it. All right, to find the total impedance of the circuit, all we have to do is add up the resistance in the circuit. So we have a 25 ohms resistance from here, followed by a 50 ohms inductor, right? Generally, inductor is a complex part of the circuit, and the equation for the total resistance is written as Z, equal to 25 plus J15. We have an inductance here, so hence it is a plus there. However, I'll show you an example after this in which there's a capacitance which will make the plus into a minus. So we'll look into that later there. So hence, to calculate from here into like the Cartesian form, we do is under root 25 square plus 15 square, which gives us 29.15. And to find the angle in which the current lags, it's an inductance circuit, hence the current will be lagging in the circuit. To find the angles, we do is tan inverse of 15 divided by 25. So that gives us in degrees. Make sure you guys, the calculator is in degrees. Some radians might be a little different, so we're just going to be dealing mostly with degrees in this case. So just make sure your calculator is right there, and it is written just like this: 29.15 angle 30.964. Hence it means that current is lagging by 30 degrees in this case, in our case for this circuit. And I told you guys about this one right here. The theta is the angle just we represent right now, that is 30 degrees. So as we see, angle in this equation is positive for current lagging the voltage and negative for leading the current. Hence, we have an inductor just to make sure your calculations are right. You can always make sure that the total impedance angle, if you have an inductor, should be a positive angle. Hence, we can see from this that it's going to be it's an inductance circuit. Okay. Moving forward, solving the equation like V is equal to IR, the basic equation, and then we find this current in the whole circuit first of all. So we have given VRMS, so that is 10 followed by 0 degrees. So current doesn't have any because the source, generally source have 0 degree to begin with. And then we have the polar and the Cartesian, we converted them to the normal, and then you just solve it. Let me know if you guys want to see the detailed steps for this. I can put another document showing how it's done, or we can just do a Zoom call to how to reach to this point. Okay, and then we find the current to be this much, which is 342.99, approximately 343, with an angle of minus 30.964. However, we have to remember in this case, like when we find the complex power, we always use I conjugate. So we do a conjugate of that, and the only thing that changes is the sign of an angle. Imagine a case that it was a negative, it was a positive here, then the conjugate becomes a negative angle here too. Well, it's opposite for this case. I'll show you another example in which it is opposite. So we can focus on that later. So then we have this right here. Then it's just a basic calculation. P is equal to VI. We have S in this case being a complex power. And oh yeah, and one more thing. To make sure that your answer is right, you can always look at the this one right there, like the real power. Give me 1 second here. Okay, it's not at this stage. Okay, so we just continue along with the problem. S is equal to VI. Then we use the same thing. In this case, you just simply multiply each other. It's generally easier in this form. You can just multiply 10 times 342.99 and then just add up the angles if there is any angles. Or you can just convert into the other form and just plus the real terms plus the imaginary terms if there are any. Like, let me know if you guys want to see in detail steps for this. All right, so we get the complex power here. So 2.94 watts plus J 1.76 VAR. So we can see from here the real power, is 2.94 and 1.76 is the reactive power that is not used by any element. We will touch on that later. I'll explain a little bit more in detail about them. So we can see from there. Oh, and just to check your answer for this, so as we see here, the S is 3.49 angle 30.964. To see if you get the right answer, you can always make sure that the angle is the same as the total impedance angle we have up here, which is right there. It means that they should be the same. This is a great way to check your work. You can always make sure that your calculations were right and you can proceed from that. As usual, please let me know if you have any questions, and I'm moving a little fast, I feel like, on this one. All right, so a similar example, but now we have a capacitance here with the resistor. As I said earlier, we write the total impedance in a similar way. However, it's just going to be a little different right now. So we have 25 minus J20 at this point. So Z, and then we do the same thing, under root 25 square plus 20 square, that gives you 32.16. However, when you're finding theta this time, you do tan inverse of minus 20 divided by 25. Hence, you will get a negative angle there. It means that the current is leading the voltage in this case by minus 38 degrees or 38 degrees, we can say. So because it is a capacitance circuit, we have this thing here at this point. All right, so and then we move again to the basic calculation, which is we are calculating the current in the circuit, Vrms 0 angle divided by 32.16 with negative 38.66 degrees, and we get the current to be 312.35 milliamperes, angle 38.66. And as we said before, we use the conjugate term in there, so I conjugate it. Only thing changes again is just the angle, so from positive it becomes negative in this case. So we have 312.35 milliampere angle negative 38.66, and we go again to find the power in the same steps, same usual steps, and we have the following answer at this point. So it's 2.44 minus J 1.95 or 3.12 angle minus 38.66. And in the similar as the last example, we can always check the angle of the impedance here to make sure it matches the impedance angle here. So we know that the answer is correct, or it's just one way of making sure it is on the right track. Alright guys, so a little bit of reactive power and active power. Give me 1 second, guys. I'll get on it. Okay, as we said before, reactive power is usually the useless power that is neither consumed or does any useful work in the circuit. Is generally generated when the it's is generally generated back and forth when the current goes back and forth from the circuit. Basically, there is an AC generator we have on one side, and there is a motor that is rotating. So the line that connects the generator to the motor, we will have a power that is going both directions from that. So the power going from the generator and a power that is coming back from the motor towards the generator. So we have two of them right there. Generally, like when we generally measure the power of a circuit, we're only measuring the real power. As it's said here, the wattmeter does not measure the reactive power. The power is generally consumed by the reactive elements that are the inductors and capacitance in the circuits. So it's written in different ways from the real power. So real power has a sign of watt, W, but reactive power is written VAR, voltage ampere reactive, basically. So basically what happens is the coils of the motors are reactive. The motor that the generator rotates, they're reactive. The current that comes in causes the magnetic field to expand around the coils when the motor is rotating during one portion of the alternative. Let's say when the power is going in, the coils get excited, the magnetic field expands, right? And when the negative and when the other portion of the AC current goes in, the magnetic field collapses on the motor, which so like the AC current being produced from the generator, which is going towards the motor, creates the up and down for a magnetic field for magnetic field in the motor. Hence, like as it's an alternative magnetic field, it induces the voltage in the coil, which causes hence the motor creates its own current that is not coming from the AC generator. It's just because of the AC generator's current, we have the increase in magnetic coil, increase in magnetic field, and decrease in magnetic field, which induces voltage in it. Hence, we get current in the motor, which is flown backwards towards the generator. So we get it is even sometimes called as a wattless power. There's no energy loss, there's no heat loss, or there's no heat dissipation. That's why it's sometimes called as a wattless power. So hence we have the portion of that. I hope it's clear enough for you guys. Like, I can try better. Okay, so now active power. Active power is the power that is represented in watts and is generally consumed by the active elements of the circuit. So it's generally resistance in this case for us. And we lose this power, like this active power is lost through heat energy, mechanical energy, transmission loss, and any loss, like any other electrical loss that is associated with the circuit, is generally lost from the actual power. So generally, like when we have when we have the generator again, AC generator, and we have a motor on one side, the feeder, like the line connecting to it, AC generator generally delivers true power in one direction. As we said earlier, reactive power flows in both directions because one is coming from generator and other one is coming from motor to the generator. And in case of true power, it just flows from one way to the other, and in reactive power it flows the both ways. And the combination of true power and reactive power is called apparent power. As we can see from the Beer diagram here, see it says kilowatt, like you can just assume k watts here, or active or true power here is generally the major components in a circuit, and the reactive power is a little bit on foam that doesn't add anything to the circuit. It's just an extra there which is not being consumed, which is being consumed but not by the active elements of the circuit. And we always see that here, that the actual power is always greater than the reactive power. Even if it's a tiny amount, it's still going to be always greater in most cases. And as we have seen, it can be represented as P plus or minus Q, JQ, according to the elements in the circuit or the total impedance of the circuit. When we have an RLC circuit that consists the resistance, then we have resistance and the inductance and capacitance in all in the same circuit. And we have, okay, so we're just going to look at a little bit of power triangles, just the basics of it. I can explain to you the power triangle right here. All right. Okay, so the power triangle, we have on the it's a right angle triangle to begin with, and on the hypotenuse we generally have the apparent power, which is the addition of reactive power plus sorry, my bad, it's reactive power plus apparent power, reactive power plus real power. Yeah, so we have that right there, along with on the right side of it we have the reactive power, which is measured in VAR or represented by Q, and at the base we have the true power P, which is measured in watts. Here, however, for this true power can be written as, we can write this as P is equal to V times I times cos of the angle they have in the middle. Like the one impedance phase angle can be calculated here, and it can be calculated using this formula. Same can be done with the reactive power. Reactive power can be calculated as Q is equal to VI. Instead of cos, we have sine this time, and we have that same impedance angle right there. And that's how the power triangle is. If you might have to draw one in the future, but generally this is how it looks like. And hence it's a triangle. You can use the hypotenuse rule, like the right angle triangle use is S square is equal to P square plus Q under root P square plus Q square. In case if you want to find just one component of a power, you can always use this rule to calculate the one missing component in the circuit. And I don't think I have covered in this here, so we'll look at the power factor too. Power factor is generally defined as a ratio of active power to the apparent power. So it's P divided by Q right there. So I'm not sure if I'm going to be discussing this further. Like, it's just a small we have here. We can always come back to it here if you want. Let's see this then. Generally, when we have an AC motor that are generally of inductive type, they generally have a low lagging factor between 0.1 and 0.3. Extremely, like, that's on a light load. However, when you increase your load, like on a full load, maybe I would say generally goes to 0.8 to 0.9. So It's just a thing to keep in mind, like when you have a load, generally the power factor would be around 0.8 to 0.9 or between them. It's never higher or never lower than it. And when there's no load at all, it's between 0.2, sorry, did I say 0.1 last time? No, it was 0. My bad on the last one. It's going to be 0.2 this time, 0.2 and 0.3. So it's generally with no load or light load, I guess. Okay, voltage regulation generally happens in a transmission line. So I'm just gonna review it for you. So it's just a little basic on that. Is generally there's a voltage drop in a line of due to resistance and inductance on a line. It's because the transmission line is not resistance free. There are heat loss. There's, as we know that the loss is directly proportional to the distance. So for the voltage regulation here, yeah, so we can generally calculate is, so the result is the receiving and the voltage end is generally less than the sending voltage end. This voltage drops Vs minus Vr. This line is expressed as a percentage of receiving end voltage and it's called voltage regulation. It can be expressed in like the following way. Vs is the sending end voltage minus the Vr is the receiving voltage, hence it's going to be it's always going to be lower, and we divide it by Vr to calculate the voltage regulation percentage. Generally it's around 10% if given, if not specified in a question. Generally it is specified and it's also around 10% in the question itself. We would of course want the thing to be low as the increase in load, like if we increase the load on the receiving end, we don't want the voltage to drop so much in the line. That creates a problem along the way. There's so much current on the line, then on the receiving end circuit might burn or might even just create electrical issues on that side. The last topic, just like the last summary we'll be looking at, is the transmission efficiency. I didn't put anything for it, and I was thinking we can add or we can generally however, there's one thing quite different between transmission efficiency and voltage regulation. If we put it in terms of the other one, like voltage regulation can also be defined in another way, which is the difference in voltage at the receiving end of transmission line between the condition of no load and a full load is called voltage regulation. Hence, we can also express it as the difference in voltage at receiving end of transmission line now here's the main part, between conditions of no load and full load. This is defined as voltage regulation. This is defined as voltage regulation, and we can use the following formula to express it, where Vs is of course the sending side and Vr is the receiving end with full load on it. Alright, so I wanted to point that out because transmission efficiency is kind of similar to this, but voltage regulation is generally mostly defined towards these ones. A difference between condition of no load and full load, and this is defined as a voltage regulation. Alright, for transmission efficiency, it could be defined as the power obtained at the receiving end of transmission line power received divided by sending power. So it's a little different than that, but the concept is quite similar. So it's an efficiency. So we generally divide, it's a ratio of receiving end power to the sending power of a transmission line is known as transmission efficiency. Transmission efficiency. You can define it as in terms of mathematical ways. It can be written as Vi cos the angle there, the impedance angle there, divided by Vi cos angle on the sending side. However, this term is from the sending side, this is the receiving end of the times. It's the receiving side of the transmission line times 100%, and then we get the transmission efficiency there. Generally, transmission efficiency lies between 7 to 15%, and it can vary depending on the distance of the transmission line, which we will look into later. We have three types, that is short, medium, and long. So this is the end and the basic review of everything you guys have learned so far. Maybe in the next DGD we will look at the transformers in more detail. Professor Habash has some DGD on his website. You can always check there to see the questions there. Or I can make another video of solving how the questions are solved. And it was nice having you guys here. So, right, thank you very much, and see you next time.